What's going on, everyone? Stack lessons here. Another 20 for the practice pile. Today on retrieval metrics, foundation model API throughput, and billion vector index scaling. Read each question carefully, pick your answer in the 10-second window, then check your reasoning against the explanation. Let's dive in. Here we go. Question 1. The verb matters here. A generative AI engineer at a pharmaceutical research company is evaluating the retrieval component of a clinical trial search tool. For each query, the system returns a ranked list of up to 10 documents. Documents can be rated as highly relevant, partially relevant, or not relevant to the query. Stakeholders require that the most relevant documents appear at the top of the list, not just that relevant documents are present somewhere in the results. Which retrieval metric should the engineer prioritize? Select one. Review the answer choices on screen. The correct answer is option B. MRR rewards first position, so why not use it? NDCG DCG evaluates both the relevance of retrieved documents and the quality of their ordering in a single metric scored from 0 to 1, where 1 represents a perfect ranking. It accommodates graded relevance judgments, such as highly relevant, partially relevant, and not relevant, and penalizes systems that place highly relevant documents below less relevant ones. This directly addresses the stakeholder requirement that the most useful clinical trial records appear first. Recall DCAI measures how many of the total known relevant documents are captured in the top results, focusing on completeness but ignoring ranking order and relevance gradations entirely. Precision DCAI measures how many of the returned documents are relevant, but similarly ignores both position and relevance intensity. Mean reciprocal rank considers only the rank of the first relevant document, and does not account for the relevance of subsequent documents, or the distinction between highly and partially relevant results, making it unsuitable when multiple graded relevance levels matter. Let's slow down here. This one tests whether you can match a metric to exactly what your system needs. Imagine you're building a clinical trial search tool. A doctor searches for diabetes treatment outcomes and gets 10 results back. Some trials are highly relevant, some are only partially relevant, and some are useless. The doctor only reads the first 3, so you need the best stuff first, and you need to score the gap between those relevance levels. That's where NDCG at 10 wins. Mean reciprocal rank only cares about your first relevant hit. It ignores everything after that. Recall at 10 just checks whether all relevant docs appear in the top 10. Order doesn't matter to it. When graded relevance plus position both matter, reach for NDCG. That's the pattern the exam tests. Here we go. Question 2. Convert the story into selection criteria. A generative AI engineer at Skyline Analytics is preparing to launch a new LLM-powered research assistant. During the initial rollout, traffic will be low and unpredictable as the team runs pilots with a handful of users. Within 6 months, they expect to scale to thousands of daily active users with consistent, high-volume usage. How should the engineer approach foundation model API billing to best match the deployment lifecycle? Select one. Review the answer choices on screen. The correct answer is option C. 20 pilots today, thousands of users in 6 months. Pay-per-token billing carries no upfront commitment and is the recommended starting point for early-stage and low-traffic scenarios where usage is unpredictable. Provisioned throughput is recommended for all production workloads with high, consistent volume because it guarantees a minimum tokens per second rate and offers better cost efficiency at scale. Transitioning from pay-per-token to provisioned throughput as the workload matures is the standard lifecycle pattern. Starting with provisioned throughput during a low-traffic pilot wastes budget on reserved capacity that sits largely idle. Using pay-per-token exclusively at high volumes is less efficient than the guaranteed throughput and better per-token pricing that provisioned throughput provides in production. Next up, question 3. one detail changes the answer. A generative AI engineer at Woodgrove is transitioning a customer support LLM endpoint to production. Baseline expected traffic is 5,000 tokens per second, but the workload is bursty and can spike to 11,000. The engineer wants autoscaling with an enforced upper boundary to contain costs. Which configuration approach should they use? Select one. Review the answer choices on screen. The correct answer is option C. Two parameters define the entire autoscaling band here. Provisioned throughput is the recommended serving mode for all production workloads, and setting both min_provisioned_throughput and max_provisioned_throughput provides autoscaling behavior with a defined cost ceiling. The minimum absorbs baseline demand without cold starts, and the maximum prevents runaway scaling during unexpected traffic spikes. A fixed peak allocation of 11,000 tokens per second eliminates autoscaling entirely and reserves expensive capacity at all times, including during low traffic periods where baseline demand is only 5,000. Pay-per-token serving with billing alerts is reactive rather than preventive, and does not provide the throughput guarantees or latency predictability that a production endpoint requires. Applying AI gateway rate limits to a pay-per-token endpoint caps inbound request volume, but provides no dedicated capacity or latency SLA for a high-throughput production workload. Next up, question 4 starts now. A generative AI engineer has developed two candidate prompt templates, V1 and V2, for a RAG-based technical documentation assistant, and wants to determine which template produces more helpful, accurate responses across a curated test dataset. They plan to use MLflow's LLM as a judge capabilities. Which evaluation methodology is most appropriate for this comparison? Select one. Review the answer choices on screen. The correct answer is option C. Single output scoring sounds rigorous, but misses head-to-head signal. Pairwise comparison is purpose-built for directly contrasting two candidate outputs. By presenting the query and both responses to the judge simultaneously and asking it to select the better one, this methodology captures relative quality differences and produces judgments that align more closely with human preference than independent scoring does. Single output scoring evaluates each response in isolation, which introduces inter-run variance and score compression near the top of the scale. When two templates produce similarly strong responses, these aggregate averages often fail to discriminate between them reliably. Retrieval groundedness measures whether a response is supported by retrieved context and is a RAG faithfulness metric, not a mechanism for comparing prompt template quality. GEval with chain of thought is a single output technique in which the judge reasons step by step before assigning a score to one response. It is not designed for head-to-head comparison of two candidates and shares the same instability drawbacks as other pointwise scoring methods. Next up, let's work question 5. Quick check. A generative AI engineer has built a RAG application that summarizes financial news articles. The evaluation team prepared 150 reference summaries written by senior financial analysts. They want to measure how closely the LLM-generated summaries match these references in terms of content coverage and fluency. Which evaluation approach is most appropriate given the availability of expert reference summaries? Select one. Review the answer choices on screen. The correct answer is option A. Expert reference summaries exist, The metric family is clear. When expert reference summaries exist, Rouge and Blur provide quantitative, reproducible measures of content overlap between generated output and references. Rouge captures recall of n grams from reference texts while Blur captures n-gram precision, and both are standard benchmarks for summarization evaluation with ground truth. Retrieval recall at K evaluates the quality of the retrieval step, specifically whether the correct source document was fetched, and does not measure the quality of the generated summary text. Perplexity is a training time metric that measures how well a model predicts held-out training tokens and has no direct relationship to inference time summary quality. LLM as a judge is a reference-free approach most valuable when human references do not exist. When 150 expert references are available, direct comparison via Rouge or Blur provides more precise and interpretable scores than having another LLM score outputs subjectively. Graded relevance demands NDCG. Strict completeness demands recall. Pay per token is the pilot default. Provision throughput is the production default. When expert reference labels exist, Rouge and Blur outperform an LLM as judge. Now, let's get into question 6. A generative AI engineer at Northgate Analytics needs to register a trained demand forecasting model to Unity Catalog using MLflow.register_model. The model should be placed in the analytics schema within the prod_catalog under the name demand_forecaster. What is the correctly formatted name argument for the registration call? Select one. Review the answer choices on screen. The correct answer is option A. 3 levels, 1 separator. Read the format carefully. Unity Catalog enforces a 3-level delimited namespace for every managed object, including registered models. The required format is catalog.schema.model_name, so prod_catalog.analytics.demand_forecaster is the correct argument. Providing only demand_forecaster without catalog and schema qualifiers either resolves to the legacy workspace level registry or raises an error because MLflow 3's default registry URI is Databricks UC, which requires fully qualified 3-level names. Forward slashes are path separators in file systems and object storage, but are not valid namespace separators in Unity Catalog syntax. Passing them causes the registration call to fail with a parse error. Colons are equally invalid as namespace delimiters for Unity Catalog objects and produce the same registration failure. Let us keep moving. Question 7. Map the qualifier to the answer. A generative AI engineer is designing an evaluation framework for a RAG-based regulatory compliance assistant used at a pharmaceutical company. For every query, a complete set of relevant documents must be retrieved because missing even one applicable regulation could result in a compliance violation. Which retrieval metric is most appropriate as the primary evaluation signal? Select one. Review the answer choices on screen. The correct answer is option A. Missing one regulation causes a violation. Which metric catches omissions? Recall at K directly measures what fraction of all known relevant documents appear within the top K results. When completeness is critical and missing a document carries serious consequences, recall at K is the appropriate primary metric because it quantifies how many of the must-have documents are being surfaced, regardless of how they are ordered. Precision at K measures how many retrieved results are relevant, but provides no signal about whether any relevant documents were missed entirely. A system could achieve perfect precision at K while still omitting important regulations. NDCG at K and DCG at 10 both evaluate ranking quality and relevance intensity, rewarding systems that position the most relevant documents at the top. These metrics are valuable when rank order matters, but neither directly measures completeness or reveals whether a specific required document was absent from the retrieved set. Time for another one. Question 8. Identify the business need first. A generative AI engineer at Castleton Insurance needs to integrate an external open AI model into their Databricks RAG pipeline while maintaining unified PII filtering, usage cost tracking, and governance over all model calls from a single control plane. Which approach should they take? Select one. Review the answer choices on screen. The correct answer is option B. PII filtering, cost tracking, governance, from one control plane. Databricks AI Gateway supports registering external model providers such as OpenAI as managed endpoints, centralizing governance over all model calls in a single control plane. PII filtering, safety guardrails, rate limiting, and usage cost tracking all apply automatically to every request routed through the gateway, eliminating the need to build these controls separately. Calling the OpenAI API directly from a notebook bypasses all Databricks governance, monitoring, and PII protection capabilities entirely. A custom proxy model on model serving can technically relay requests, but requires manual implementation of every governance feature, rate limiting, PII filtering, usage tracking, that AI Gateway provides natively, creating significant maintenance overhead. Periodic batch pulling of responses from OpenAI into Delta tables is asynchronous and unsuitable for real-time RAG inference, and still provides no unified governance layer. Time for another one. Question 9. Compare the distractors carefully. A generative AI engineer is explaining the 3 core steps of a RAG pipeline to a new team member who believes that augmentation means running the user query through the vector store a second time to retrieve additional documents. Which statement accurately describes what the augmentation step does in a RAG pipeline? Select one. Review the answer choices on screen. The correct answer is option D. Augmentation is not a second retrieval pass. Watch the definition. In a RAG pipeline, augmentation is the step between retrieval and generation. It takes the supporting documents returned by the retrieval step and combines them with the user's original query inside a prompt template. This structured combination forms the complete, context-enriched input that is then passed to the LLM for response generation. Running the query through the vector store again would be an additional retrieval step, not augmentation. Passing retrieved documents to the LLM without any structuring omits the prompt template that shapes how the model should interpret and use the context, typically resulting in lower quality or inconsistent responses. Fine-tuning. The embedding model is an offline training operation that occurs before deployment and has no role in what happens during an active query in a live RAG pipeline. Ready. Question 10. The setup controls the answer. A generative AI engineer at Ashford Commerce built an internal knowledge assistant piloted successfully by 20 engineers. The company is now rolling out the assistant to its 3,500-person workforce, with sustained high concurrency expected throughout business hours and strict response time requirements. Which model serving configuration should the engineer choose for this production deployment? Select one. Review the answer choices on screen. The correct answer is option A. 20 pilots worked, but 3,500 daily users demand reserved capacity. Provisioned throughput endpoints allocate dedicated inference capacity and are Databricks' recommended configuration for all production workloads. Configuring minimum and maximum provisioned throughput values guarantees consistent latency under the sustained high concurrency load expected from a 3,500-person workforce. Pay-per-token endpoints lack reserved capacity and latency guarantees under heavy sustained load. They are recommended for initial development and low-traffic use cases, not large-scale production rollouts. An external model endpoint through AI Gateway introduces third-party dependency and additional network round trips, and cannot provide the reserved capacity needed for guaranteed performance at scale. A serverless endpoint that scales to 0 introduces cold start delays when traffic resumes after idle periods, violating response time requirements for an always-on workforce deployment. Unity Catalog demands strict delimited notation. Slashes and colons both fail registration. AI Gateway is the single control plane for external models, PII, cost, and rate limits in one place. Augmentation is prompt construction, not a second vector lookup. Let us switch gears. Question 11. Classic exam trap. A generative AI engineer at Cobalt Systems is configuring a provisioned Throughput Foundation Model API endpoint for an internal assistant that handles 10,000 queries per minute with strict latency requirements. Which two parameters must they specify when creating the provisioned Throughput endpoint configuration? Select 2. Review the answer choices on screen. The correct answers are option B and option D. Select 2, and the retrieval fusion parameter is a planted distractor. Provisioned throughput endpoints on Databricks require both min_provisioned_throughput and max_provisioned_throughput to define the reserved capacity range in tokens per second. The minimum value sets the guaranteed floor that Databricks always keeps allocated for the endpoint, ensuring latency is consistent even during traffic spikes. The maximum value sets the upper bound of auto-scaling, controlling cost exposure. Both values must be specified together to establish the valid throughput band. Sampling_fraction is a parameter for inference table configuration that controls what fraction of requests are captured for logging, not a provisioned throughput setting. Max_concurrent_requests is a general serving parameter related to queue depth and is not the mechanism Databricks uses to express provisioned capacity for foundation model APIs. RRF_param is the reciprocal rank fusion parameter used in hybrid AI search queries to control the weighting between keyword and vector results and has no relationship to model serving throughput configuration. Let's slow down on this one. Two required parameters sounds simple, but the decoys are sneaky. Think of provisioned throughput like reserving a lane on a highway. You tell Databricks, always keep at least 850 tokens per second ready, and never exceed 2,400. That pair, min and max, locks in your latency floor and your cost ceiling. The question has 3 decoys. The RRF_param comes from hybrid search. It blends keyword and vector results, not a model-serving param. Sampling_fraction controls what share of requests get logged to a table. Max_concurrent_requests manages request queuing. It's not the provisioned capacity field. Must specify is the key qualifier. Only those 2 throughput bounds are truly required. Let us switch gears. Question 12. Look for the constraint that matters. A generative AI engineer at Northwind Healthcare is deploying an LLM-powered patient intake assistant. The assistant collects symptom descriptions from patients and queries a medical knowledge base. Compliance requires that patient-identifiable information such as names, social security numbers, and phone numbers never appear in LLM responses sent to third-party analytics dashboards. The engineer wants to enforce this requirement at the infrastructure level without modifying application code. Which AI gateway feature should they configure? Select 1. Review the answer choices on screen. The correct answer is option D. No application code changes, only infrastructure enforcement satisfies compliance. AI Gateway's PII detection and redaction feature automatically identifies and replaces personally identifiable information, including emails, social security numbers, and phone numbers, with placeholders before the response reaches the caller. This enforcement happens at the infrastructure layer, requiring no changes to application code. Rate limiting controls request volume and is designed to prevent cost overrun or protect service availability, not to scrub sensitive data from outputs. Safety filtering targets harmful content categories such as hate speech or violent content, and would not identify specific PII fields like SSNs or phone numbers. Traffic tracking logs full request and response payloads for audit purposes, but does not modify or redact any content. Let us switch gears. Question 13. Make the distractors prove themselves. A generative AI engineer at Thornwood Commerce is building a global product recommendation engine. The AI search vector index will store embeddings for over 2 billion product listings at 768 dimensions each. During recent catalog refresh cycles, the team identified that indexing speed is a critical bottleneck slowing down updates. The engineer needs to select the endpoint type that best handles this scale and resolves the indexing throughput problem. Which endpoint type should they choose? Select one. Review the answer choices on screen. The correct answer is option D. One distractor inverts the latency trade-off. Catch it before clicking. Storage-optimized endpoints are designed for vector stores exceeding 1 billion vectors and provide 1020x faster indexing than standard endpoints, which directly addresses the bottleneck during catalog updates. Standard endpoints scale to approximately 320 million vectors at 768 dimensions, making them insufficient for 2 billion product listings regardless of how many replicas are added. Replicas distribute query load but do not expand the fundamental capacity limit. Reducing embedding dimensions affects retrieval quality and does not change the capacity constraints of a standard endpoint. Storage-optimized endpoints actually introduce approximately 250 milliseconds of additional query latency, compared to standard endpoints, the opposite of the claim in the fourth option, making it important to accept this trade-off when scale and indexing throughput are the priorities. Let's slow down here. The endpoint capacity numbers are what make or break this question. Picture 2 billion product listings, each needing a fresh embedding every catalog update. Your indexing pipeline is the bottleneck. Here's the key number. Standard endpoints cap at roughly 320 million vectors. That's it. Adding more replicas won't help. Replicas spread query traffic, not storage. You need the storage-optimized endpoint, which handles over 1 billion vectors and indexes 10 to 20 times faster. Now the trap. Option B says storage optimized reduces latency by 250 milliseconds. That's backwards. It actually adds 250 milliseconds of query latency, the cost of the scale. When your catalog is 2 billion listings, you pay that latency tax and move on. The exam rewards knowing the direction of that trade-off. Keep your focus here. Here is question 14. A generative AI engineer at Westfield Data is building a RAG application with LangChain. They need to connect a Databricks-hosted embedding model to generate query embeddings, retrieve relevant documents from a Databricks AI search vector store, and pass retrieved context to a Databricks-hosted LLM for answer generation. Which combination of LangChain components correctly implements this end-to-end pipeline? Select one. Review the answer choices on screen. The correct answer is option B. 3 Databricks native LangChain components, 1 end-to-end pipeline. LangChain provides native Databricks integrations for all 3 pipeline components. Databricks embeddings connects to any Databricks Model Serving endpoint that exposes an embedding model, enabling query time embedding using the same model used to index the corpus. Databricks Vector Search integrates directly with Databricks AI search indexes and functions as a LangChain retriever, handling similarity queries and returning ranked document chunks. Chat Databricks connects to Databricks-hosted LLMs via the Model Serving API, and is the correct interface for the generation step. Using OpenAI embeddings or FACE introduces external dependencies that bypass Databricks' native infrastructure and risks embedding dimension mismatches with the existing AI search index. Using a custom REST API retriever duplicates functionality that Databricks Vector Search already provides natively, adding unnecessary maintenance overhead. Chat Databricks is a chat model interface designed for text generation from prompts. It cannot produce embeddings, and combining it with a prompt template does not replace the dedicated embedding and retrieval components that the pipeline requires. All right. Question 15. Keep the constraints in view. A generative AI engineer at Heathrow Legal is building a case law search system. Attorneys need precise paragraph-level citations so they can pinpoint exact sources, but the LLM requires broader document sections to generate accurate legal summaries without losing surrounding context. Which chunking and retrieval strategy best satisfies both requirements simultaneously? Select one. Review the answer choices on screen. The correct answer is option A. Attorneys need paragraph citations. The LLM needs broader surrounding context. Parent-child retrieval separates the indexing granularity from the generation context granularity. Small chunks of approximately 512 tokens are indexed in AI search, enabling precise paragraph-level recall for attorney citations because the search space is fine-grained. When a matching chunk is retrieved, the system fetches its larger parent segment of approximately 2,048 tokens to supply to the LLM, giving the model sufficient surrounding context to generate accurate summaries without missing adjacent information. Indexing only with large chunks improves LLM context, but degrades retrieval precision, making it harder to pinpoint the exact paragraph an attorney needs for a citation. Semantic chunking creates coherent variable-size segments, but does not inherently separate the citation resolution from the context provisioning, returning the same chunk to both the attorney interface and the LLM forces a trade-off where either precision or context richness is compromised. Indexing full documents without chunking is impractical for large legal corpora, where documents can far exceed model context limits, and retrieving entire documents wastes context window space on irrelevant content while still failing to surface pinpoint paragraph-level citations. Let's slow down on this one. Parent-child retrieval is exactly what the exam is testing here. Imagine you're an attorney hunting for one exact sentence in a 200-page judgment. You need it pinpointed, not a section, not a chapter, but your AI also needs a full 3-paragraph section to write an accurate summary. Those are two different jobs. One-size chunking forces a compromise. Use 512 token chunks and search is sharp, but the LLM loses context. Use 2,048 token chunks, and the LLM gets enough context, but pinpointing a paragraph becomes guesswork. Parent-child retrieval splits the two jobs. Index with small chunks for precise search, then pull the bigger parent chunk to feed the LLM. 1 retrieval, 2 granularities. That's why option A wins. Provisioned throughput requires both min and max. Neither parameter alone is sufficient. Storage-optimized endpoints add roughly 250 milliseconds of latency rather than removing it. Parent-child retrieval decouples citation granularity from generation context width. All right, question 16. The clue is not in the service name. A generative AI engineer needs to evaluate retrieval quality for a knowledge management system where documents range from not relevant to highly relevant in varying degrees. The engineer wants a metric that captures both the intensity of relevance and whether highly relevant documents are ranked near the top of the results list. Which metric should they use? Select one. Review the answer choices on screen. The correct answer is option B. Graded relevance scale plus rank discount. One specific metric owns both. DCG at 10, Discounted cumulative gain at rank 10 is the recommended metric when documents have graded relevance levels. It uses a 0 to 3 relevance scale to capture intensity, not just whether a document is relevant, but how relevant it is, and applies a logarithmic discount that penalizes highly relevant documents appearing at lower ranking positions. This makes it the right choice when both relevance intensity and ranking order matter. Recall at K measures completeness of retrieval but treats all relevant documents equally and ignores ranking position. Precision at K also treats relevance as binary and does not account for where highly relevant results appear within the list. Cohen's kappa evaluates consistency between two raters and is used to validate LLM as judge alignment with human judgment, not to measure the retrieval system itself. Okay, question 17. Read this one twice. A media startup is building an automated content moderation pipeline that must analyze both uploaded thumbnail images and short preview video clips to detect policy violations and generate structured violation reports. The team wants to use a single foundation model API model that natively handles both input types without additional pre-processing pipelines. Which model should they use? Select one. Review the answer choices on screen. The correct answer is option C. Claude handles images well, but can it natively process video clips? Gemini 2.5 Flash is the correct choice because Gemini family models available through the Foundation Model API natively support all 4 input modalities: text, image, video, and audio. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. Let's slow down here. The video modality question is the whole trick on this one. Imagine you're building content moderation for a streaming platform. You need to flag bad thumbnails and bad video clips, ideally in one API call, no extra pipeline. That's exactly what this question tests. Gemini 2.5 Flash is the only model here that natively handles video. Claude Sonnet 4 is strong, but it only takes text and images, not video. Llama 4 Maverick, same story. Text and images only. BGE Large is an embedding model that converts content into search vectors. It can't understand video or write violation reports at all. Only Gemini 2.5 Flash covers all 4 input types: text, image, audio, and video. That's the only answer that clears the bar. Okay. Let's open question 18. A generative AI engineer is running a series of fine-tuning experiments on a domain-specific language model using MLflow. For each run, they need to record 3 things: the learning rate and batch size configured before training begins, the validation loss captured at the end of every training epoch, and a short label identifying which dataset version was used. Which approach correctly matches each piece of information to its appropriate MLflow logging call? Select one. Review the answer choices on screen. The correct answer is option D. Parameter, metric, tag, each maps to a distinct MLflow function. MLflow distinguishes 3 types of run metadata by their nature and mutability. Parameters are static configuration values set before a run begins. Hyperparameters such as learning rate and batch size are the canonical example and are recorded with lflow.log_param. Once written, parameter values cannot be changed, which reflects that they represent fixed inputs to a run. Metrics are numeric values that may change over the course of a run and can be associated with a step index, making per-epoch validation loss a natural fit for lflow.log_metric, which supports step-based time series that LFlow renders as training curves in the UI. Tags are free-form string key-value pairs used to annotate runs with contextual metadata such as dataset version labels, team identifiers, or experiment purpose, and are set with MLflow.set_tag. Swapping parameters and metrics forces the system to treat learning rate as a time-varying quantity and validation loss as a static preset, destroying the step-based metric history and making cross-run comparisons incoherent. Using MLflow.log_artifact for configuration values stores them as opaque file blobs rather than structured, queryable run metadata, eliminating the ability to filter and sort runs by hyperparameter values. Here we go. Question 19. The wording narrows the answer. A generative AI engineer is evaluating the retrieval component of a clinical decision support (RAG) system. The system must surface every relevant drug interaction guideline for a given patient medication list. Missing even one relevant guideline could lead to a harmful recommendation. Which retrieval metric should be the primary optimization target? Select one. Review the answer choices on screen. The correct answer is option C. Missing a drug interaction guideline is catastrophic. Maximize which metric? Recall at K measures the fraction of all known relevant documents that appear in the top K retrieved results, ranging from 0 to 1, where 1 indicates all relevant documents were returned. In safety critical scenarios where omitting any relevant guideline is unacceptable, maximizing recall is the appropriate primary objective. Precision at K measures the proportion of retrieved documents that are relevant, which penalizes noise but does not account for omissions. A high-precision retriever could score well while still missing critical guidelines entirely. NDCG at K rewards placing highly relevant documents near the top of the ranking list, but does not specifically penalize documents that fall entirely outside the top K window. Mean average precision averages precision at each recall level, but does not emphasize completeness as directly as recall. Here we go. Question 20. Anchor on the exact workload. A generative AI engineer at Dunmore Analytics is building a large-scale semantic search system over a corpus of 1.8 billion product descriptions. The team configured a standard AI search endpoint and finds that delta sync operations consistently exceed 20 hours, creating an unacceptably long window before newly updated products are discoverable. Current query latency is well within acceptable bounds, and the team can tolerate a modest increase of up to 300 milliseconds per query. Which endpoint configuration resolves the indexing bottleneck while remaining within the stated latency tolerance? Select one. Review the answer choices on screen. The correct answer is option C. Latency tolerance is stated explicitly. Use it as your decision gate. Storage-optimized endpoints are specifically designed for corpora exceeding 1 billion vectors, providing 10 to 20 times faster indexing throughput compared to standard endpoints, which directly resolves the 20-hour sync window. The trade-off is approximately 250 milliseconds of additional query latency, which is within the 300 millisecond tolerance the team explicitly accepted. Distributing the corpus across multiple standard endpoints reduces the per-endpoint vector count, but does not eliminate the fundamental indexing throughput limitation that exists at the standard tier for very large collections. total indexing work remains the same. Switching to a direct access index shifts the responsibility for embedding computation and ingestion to the application team and changes the pipeline architecture, but it does not provide the hardware-level indexing speed improvements that storage-optimized infrastructure delivers. Reducing embedding dimension from 768 to 256 decreases vector precision and degrades retrieval quality in exchange for a moderate storage reduction, addressing size rather than the indexing throughput constraint. 3 takeaways from this session. First, NDCG DCG is correct when both graded relevance levels and ranking position simultaneously matter. Recall DCG is the right primary metric when missing any single document is unacceptable. Second, provisioned throughput requires both min_provisioned_ throughput and max_provisioned_ throughput. The pay per token to provision transition is the canonical pilot to production lifecycle. Third, storage-optimized AI search endpoints deliver 10 to 20 times faster indexing for corpora exceeding 1 billion vectors, but add approximately 250 milliseconds of query latency, a deliberate trade-off. These 3 clusters, retrieval metrics, provisioned throughput, and billion vector indexing, are the production stack this exam tests hardest. Know the trade-offs, not just the answers, and you are ready.